We've talked about solving systems of equations by graphing and by substitution. Today we're going to talk about the best way to solve systems, the most robust, and the one that is the best going forward in future math classes. So this method is called solving systems by elimination. And it's based on an idea that we'll talk about the process down below, but this graphic illustrates kind of the idea, is that I have 2 reds is equal to 1 blue. These are balanced, neither side is like heavier than the other one. So we know that with an equation, if I had something like 4x equals 3, I'm allowed to add something or subtract something from both sides as long as it stays in balance. So I could change this to 4x plus 7 equals 3 plus 7. That doesn't unbalance the equation because I've added the same amount, 7, on both sides. In the graphic, though, we're adding shapes. So 2 red and 1 blue are in balance. Likewise, a red and green balances a yellow. So that's just like saying those things are equal to each other. So if I take a red and a green and add it to the 2 reds, and I add the yellow to the blue, then everything should still be in balance. Because even though red, green, and yellow aren't as simple looking as plus 7, it's the same idea. I'm adding something to each side that is in balance, that's equal. So now when I have red, 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 green, it's still equal to blue, yellow, because the amount I added to each side had the same total weight. So that's our idea here, and the way we do it is actually really simple, and you don't even need to think about the why that we're allowed to do, but we're adding together equations in order to solve things. So we have some steps here that we're going to follow, and then we'll do some examples using them more. But these 6 steps are the way that we're going to solve using elimination, and this is going to let us solve more complicated equations, and it will always be a valid method, whereas substitution sometimes gets really ugly. So substitution seems nice on the surface, but we only saw examples where there was a variable that's easy to isolate. If I wanted to isolate one of these 4 variable terms to get a single x or y, I would end up with some really terrible fractions within this equation. So say I wanted to solve this one for y, I have to divide by 3. Then I have y equals negative 2/3 x plus 7/3, and then I have to substitute that in for y here. So I'm multiplying negative 4 times these numbers of thirds, and it just gets really, really ugly. So rather than doing that, we're going to use this new method called elimination. The first thing we do is we rearrange our equations so that they line up. Because, just like the little mobile diagram with the balance up in the warm-up, we're going to be adding these 2 equations together. So an easy way to do that is to put things in standard form. So notice this second equation is already in standard form. So I'm going to rearrange the first one by adding 2x to both sides. So I'll do that over here. 2x plus 3y is equal to 7. And then we have, I'm going to do this one in a different color, 5x minus 4y is equal to 6. Now that these things are lined up, remember like in the mobile up above, I can add 5x minus 4y to the left side and add 6 to the right side, and everything will stay in balance because 5x minus 4y is the same amount as 6. So if I add that to the left and that to the right, we get the same thing. The thing is, if I add these together right now, I get 7x minus y is equal to 13, which isn't really better than what we already had because there's still 2 variables. And the whole thing with an equation is I can only solve an equation for one variable. So that's close to the right idea, but we need another step before we get where we're going. So step 2 says we're going to multiply our equations by something so that we match up one of our variables. In this case, we could multiply there's an example here multiplying by 5 and -2. I'm actually going to go the other way just for a different example than what's written there. I want to match up these. So I want to have 12y and -12y. That way, when I add the two equations together, I'm going to end up with no y's, and I'll be able to solve for the remaining variable, which is x. In order to do this, I need to multiply the top equation by 4 and the bottom equation by 3. You see over here, you could also use 5 and -2 to eliminate the x's. It doesn't matter which variable we eliminate first, we still have to solve for both anyways. So multiplying my blue equation by 4, it becomes 8x plus 12y equals 28. Remember to multiply all the terms by 4. Don't miss any. It's common to multiply the x and y and then leave this as 7 and forget to multiply that c term, or to multiply just the one you cared about, the y and this constant, and forget about the x. So just don't forget about any of them. Make sure everything gets multiplied. My second equation becomes 15x minus 12y is equal to 18. Then we add the two equations together. So I add 15x minus 12y on the left and add 18 on the right, so everything stays nice and balanced. So on the left, I get 23x. 12y minus 12y cancels out. I get no y's, and that's the entire idea here. And then on the right, 28 plus 18 is equal to 46. So I divide by 23 and find that x is equal to 2. Now that I have x equal to 2, the rest of the process here feels just like what we did with substitution, because now I need to use my two original equations to find y and to check my solution. So I'm going to use the blue equation to plug in x, so 2 times 2 plus 3y is equal to 7. I subtract 4 from both sides and get 3y equals 3, y equals 1. So my proposed solution is 2, 1. But I want to use the green equation to check it. So I'm going to plug into this green equation up here my solutions, and we get 5 times 2 minus 4 times 1 equals 6. That's 10 minus 4 equals 6, which is true. So that checks out, and I know now that my solution is definitely correct. So it has some stuff in common with substitution, mostly that ending part. So once we've isolated one variable and solved for it, then we follow substitution rules to go and find the other variable and check our solution. It's that first part where we add the equations together and eliminate a variable that makes this method different. So that's the process, and we started with a fairly complex one. Some of them are much simpler. So let's try some more examples. If you'd like, if you understand the idea, then feel free to pause the video and go through these and then check them with me afterward. So on this first one, we're going to take 3y equals 24 minus 6x and 4x equals 18 minus 3y and align the variables. I'm going to do that by making it standard form. 6x plus 3y equals 24 and 4x plus 3y equals 18. In order to add these and have something get eliminated, I'm going to multiply the bottom equation by -1 which is just going to change all the signs. So rather than cluttering my space, I'm going to just do that and make this negative 4x minus 3y equals negative 18. You may be asking, why don't we just subtract the two equations instead of adding them? And you absolutely can do that, but you will make so many more sign mistakes if you do. It's much better to have one of your variables be equal and opposite and to add the two equations rather than trying to subtract them. Lots of sign mistakes happen when we try to subtract, believe me. Okay, so 6x minus 4x, we get 2x. 3y minus 3y, no y's. And then 24 minus 18 is 6. So our x value is 3. We're going to plug that back into the first equation. So we get 3y equals 24 minus 6 times 3. I don't know why I wrote my 3 funny. There. So we have 24 minus 18. 24 minus 18 is 6. So this tells us y is equal to 2. So our solution should be 3, 2. But just to be sure, we're going to use the green equation to check it. So we have 4 times 3, that's 12, is equal to 18 minus 6. 12 is equal to 18 minus 6, so that checks out, and our solution is correct. The second one, we already have everything lined up, and we already have a variable set to eliminate. This is a much easier question because we can skip the first couple of steps and go straight to adding the equations. We get 6x, no y's, and 54. So x is equal to 9. We plug that back into one of the equations, let's say the first one. So 2 times 9 minus 3y equals 12. This is 18, so I'm going to subtract 18 from both sides. So that equals negative 6. Y is equal to 2. We go back and plug that in to the first equation. So we get 2x minus... Wait, we already plugged in. Sorry, wait. I forgot this problem is short. So we have a proposed solution of 9, 2. We're going to plug that solution into the green equation and make sure that it works. So 4 times 9, that's 36, plus 3 times 2, that's 6. 36 plus 6 is 42, and it says equals 42. Check, that's good. Our solution is correct. The third one, we don't have anything that matches, so there's actually a couple of options. The x's already have opposite signs, so I could multiply the top equation by 4, and the x's would eliminate. But generally, whenever possible, you want to keep the numbers as small as possible. So instead of doing that, let's multiply the top equation by negative 1 and turn it into positive 2x minus 6y is equal to positive 26. Now we can add the two equations and eliminate the y's. So we get 10x is equal to negative 16 plus 26, 10. X is equal to 1. And then plug that back into one of the equations. We'll go with the first one. So negative 2 times 1 plus 6y equals negative 26. This is negative 2, so we'll add 2 to both sides. We get 6y is equal to negative 24, meaning y is equal to negative 4. So our proposed solution is 1, negative 4, and we're going to use our other equation to check it. I didn't make it green, but we'll make it green here. So we have 8 times 1, that's 8, plus 6 times negative 4, that's 8 minus 24, equals negative 16. 8 minus 24 is negative 16. That checks out, so we do have the correct solution. So these were easier because we didn't have to multiply things except for changing the signs. The more complicated ones, like our original example up here, are where we need to multiply one or both equations by something to make the variables match. So sometimes we can just multiply one of them. Sometimes we have to multiply both. So the example that we did at the beginning was the most complicated version, where we needed to multiply both equations to make one of the variables equal and opposite, so it would cancel out. These ones are going to be a little simpler, where we're just multiplying one thing. So on this example, we can again have two options, right? We can always choose to eliminate x or y. If I want the x's to eliminate, I would need to multiply the top equation by -2. That way I would have -4x here and +4x here. The alternative is to multiply the top equation by -3, so that I get -3y and +3y, and the y's eliminate. Given the choice, I will always choose the smaller number. That way, our numbers stay small and don't get out of hand. So if I have the choice of multiplying by -2 or -3, I'm always going to choose -2. Not to say -3 is wrong. You can do that, but it's not my preference. So we have -4x minus 2y is equal to -16. Again, don't forget the -2 goes to all three terms, even the 8. It's easy to forget to distribute it on the right side. Our green equation is going to stay the same. 4x plus 3y is equal to 18. When we add these together, the x's eliminate. We get a single y is equal to 2. We're going to plug that back into our first equation and get 2x plus 2 equals 8. So 2x equals 6 and x equals 3. So our proposed solution is 3, 2. We need to use the green equation to check that. So 4 times 3 plus 3 times 2 is equal to 18. That's 12 plus 6 equals 18. That is true, so that looks like we have the correct solution. All right, the ones down here all need to be multiplied by something. I think I will leave those as practice because we've already done a little bit of multiplying. Maybe we'll just look at what we need to multiply it by, and I'll leave the work for you to do all the rest of the steps. So on this first one, if we wanted to match up the y's, I would need to multiply both equations by something, because I'd need to multiply the top one by 2 and the bottom by -3. It's simpler if we only need to multiply one equation. So here, the best answer is to multiply the first equation by -4 and just match up and eliminate the x's. In the second one, this is really close to being set up properly. The signs are opposite. We just need the bottom one to be twice as big, so we'll definitely multiply this equation by 2. In this next one, we don't have anything where we can just multiply one thing. So we either need to multiply this one by 3 and this one by -5. That would match up 15x and -15x. Or we could make it so that the y's eliminate, and we could do that by multiplying by 3 so that we get 12y, and -2 so that we get -12y. 3 and -2 are smaller than 3 and 5, so I would choose those as my multipliers instead of doing the x elimination, because then the numbers get bigger. So I'll leave the rest of that for you to work out the steps, and we'll finish up on special cases. So as with all equation stuff we've had this year, we have special cases for systems of equations. In case number 1 here, we have 2x plus 3y equals 9, 2x plus 3y equals 5. If we set, let's say multiply this by -1, we get -2x minus 3y equals -5. Then when we add that to the other equation, our result is 0 plus 0 equals 4, which says 0 is equal to 4. That is a false statement. And as with any equation solving, the weird special cases only happen when all the variables disappear. So since we have a result with only numbers, so there are no variables, then when we get a false result, we would say that there is no solution. If you think about this graphically, these are parallel lines. So we have 2x plus 3y equals 9. That's a slope of negative 2/3 starting at 3. So that's kind of like that. And then our other line has a slope of negative 2/3, but it starts at 5/3, which is a little less than 2. So that's here-ish. And it has the exact same slope. So since these lines are parallel, they're never going to meet, meaning if we're looking for the intersection, there isn't one. So since there's no intersection, we say there is no solution to this system because they will never cross. That only happens with parallel lines and only happens when all the variables disappear. Situation 2 is already set up for elimination. The signs are opposite. So if I add this, I get 0 plus 0 equals 0. 0 equals 0 is a true statement. So again, there's no variables, and this time we got a true solution. So if you think about graphing these two lines, the first one is 4/5 x plus 7/5. So that's something like, I don't know, like that roughly. And the second one is also 4/5 x plus 7x, or plus 7/5. So that means that is the exact same line as this one. We call these lines coincident. They're the same exact line. They're just two equations both giving you that line. And these were parallel. So when we have this coincident line, it's a little different than a normal equation where the special case said all real numbers. So all real numbers make sense when we're looking for the value of x, when we're just looking for a variable. But we can't use that here because we're looking for ordered pairs as the solution, and an ordered pair isn't a real number. Also, there are infinitely many points along this line that they share, but there's also infinite other points outside of those lines that they don't share. So we can't say everything is a solution. So the best we can do here is to say that there are infinitely many solutions. So it's not really specific about what those solutions are. It's just every point that's on this line. So infinitely many solutions is kind of our key phrase for coincident lines, where every point on the line is a solution to the system. So if it's a true statement, then our key phrase, I'll try to write it a little neater, is infinitely many solutions. And if we get a false statement, again, remember this only happens when all the variables go away, then we have no solution. And that's because this one is coincident and this one is parallel. Okay, so that covers our notes on solving with elimination. This is, generally speaking, the best method for solving systems algebraically, and it's the one you should practice and get used to the most because it always works, whereas substitution only works in cases where it's nicely set up. This one is more robust and can solve any kind of system you have. In fact, in later classes like Algebra 2, you'll use it to solve systems that have more than 2 equations. So you could solve a system of 13 equations using this method. You probably don't want to. You'd use a calculator or a computer program to do that. But that calculator or computer program, the algorithm that it goes through, would be this elimination process. So this is the way to solve systems. Although substitution in some cases, if it's set up nicely and looks good, like to use that, you can absolutely do it. But this is the kind of default best one. And then there's a Desmos activity to work on that's assigned to you in Desmos.